Another thing that we can predict from the periodic table are ionic charges. So let's go to our definition of ions and discuss ions and then see how it relates to the periodic table. So an ion, you can see here, is a charged particle. And when we talk about charge, we're talking about positive or negative. How atoms become charged is by gaining or losing electrons. Okay, so if just to remind you, an atom has two of the subatomic particles with charge that we're going to think about, protons and electrons. And protons are in the nucleus. They have a positive charge, and they're related to the identity of the atom. And then electrons are outside the nucleus in the electron cloud, and they have a negative charge. Those are related to bonding and chemical reactivity. Electrons can be lost or gained without changing the identity of the atom, but what does change is the charge. So we have positively charged ions, and those are called cations. Some people say cations, and that's fine. Now, one thing that we'll need to remember is that positive ions are formed when electrons are lost, because since electrons are negative charge, losing electrons forms a positive ion. Below there, I have some examples written. So I have I don't say how we're going to write it or how we know it, but these are just what an ion would look like. So we use superscripts when we write the charge. So that would be calcium with a 2 positive charge. We also have something called polyatomic ions, and this is where you have more than one atom that has a charge. So they're bonded together as a group, and that group has a charge. And this particular one, ammonium, has a +1 charge. I want you to note that 1 is not written. And that's also true with negative charges. If it's the number 1, it won't be written. Okay, we can also have negatively charged ions, because positive and negative. Negatively charged ions are called anions, and anions occur when an atom gains electrons. Again, electrons are negative, so when you gain negative, it will become a negative ion. And below I have 2 formulas, examples of how an ion would look when it's negative. So there's the chloride ion that has a 1 negative. And then below it, this is the polyatomic ion, the sulfite ion. Sorry about that big bark. That was one of my dogs. Okay. So let's keep going with ions. So this page is just the definition, the words we use when we're talking about positive and negative ions, and how they might look when we write the formula. But let's get into how we would predict, especially for the representative elements using the periodic table, what the charges would be. So the rule or the idea that we'll use to predict the charges of the representative elements is called the octet rule. So the octet rule, which you can think of as 8, says, as you can read here, that elements are going to gain, lose, or share valence electrons to look like the electron configuration of a noble gas. Remember, the noble gases have full outer shells. That means they have 8 electrons in their outer shell or their valence shell. This is a very stable electron configuration, and so the other elements try to reach that by gaining and losing their electrons. And so this is what we use to help predict the charges of the representative or main group elements. So this is just to connect the ideas. So here are the noble gases. Now I say they all have 8. Helium up here at the top does not have 8 in its valence because on the first energy level there's only an S sublevel, so helium's full at 2. So I'm not really referring to helium. It still has a full valence, but it doesn't have 8. There's no p orbital, there's not a, I guess p orbitals, yeah, there's not a p sublevel for helium. So let's look at each of these. And if you want to pause, you can try to answer at any point if you want to test yourself. But the question is, what noble gas has the same electron configuration? Another word is isoelectronic. That just means same electron configuration. So what noble gas is isoelectronic with these ions? So the first one is oxygen. So if I find oxygen, it's right here. The 2 negative says that it has gained 2 electrons. Remember, gaining electrons creates a negative charge. So oxygen, down here looking at the periodic table, is at 8, and if it gains 2 electrons, it goes 2, 9, and then 10. So oxygen would have the same electron configuration. Oh, not oxygen. Oxide ion, O2 negative, would have the same electron configuration as neon. You might notice when I named it, I didn't call it an oxygen ion. Negative ions or anions, they changed the name by adding IDE to the ending of the first part of the name. So instead of an oxygen ion, it's called oxide ion. Now letter B is magnesium. So if I find magnesium, it's right here. And it has a 2+ charge, which positive charge means that electrons have been lost. So magnesium has lost 2 electrons. So if magnesium on the periodic table starts with 12, if it loses 2, it would go like 11 like sodium and then back like neon. So magnesium also has the same electron configuration as neon. Now let me clarify. Oxide ion and magnesium ion are not changing into neon. They just have the same electron configuration. The identity of the atom is determined by the protons, and we're not changing protons, we're gaining and losing electrons. You also might notice that I called the magnesium ion the magnesium ion. Cations are named the same as the element, so their name doesn't change. And lastly this is bromide, Br, there is a -1 right there. So you find bromine, there it is. We see it has a -1 charge, which means it gained 1 electron. And so if I have bromine on the periodic table with 35 electrons, if it gains 1, it looks like krypton. Its electrons do. So this is what the octet rule is predicting, that elements are going to gain or lose electrons to have the same configuration as the noble gas that is closest to them. So for nonmetals, what it means is they will gain. Their closest noble gas is to the right of them. For the metals, they actually go to the previous period. They have to go backwards. So let's investigate that a little bit more, and then we're going to create a pattern based on this octet rule that helps us use the periodic table to predict the charges of the representative elements. So I want to just look at some electron configurations so we can develop a pattern. So here's an important concept that you can take to the bank. metals lose electrons to form cations. Okay, we want to remember this. It is helpful for us to know that metals are going to form cations. So I chose two examples, one from group 1A and one from group 2A. I'm not going to do all the elements in group 1A, just choose one example. So I chose sodium, which we've seen in a previous video. And if we look at the electron configuration and compare it to the electron configuration of the noble gas in front of it, what we notice is that if sodium would lose this one electron right here, it has the same configuration as neon. And so that's what sodium does. It loses its one valence electron, and it becomes the sodium ion. Well, the really cool thing about every element in group 1A is that they all have one valence electron. And so we can use that as a pattern and predict. I'm going to title this page. We're going to predict the stable ions from the octet rule. And group 1A, we would predict these would all be a 1 plus. Normally we don't write the number 1, but because I'm going to put them on a pattern, I'm going to. And what it tells me is I don't have to memorize all the ions. If I want to know the charge of potassium, I predict that it's a 1 plus simply because it has one valence electron that it's going to lose. Let's go back and look at the second example. So I picked one example from group 2A. I picked magnesium. Now again, notice if I look at the noble gas closest to it, which is neon, and I look at magnesium, those two parts of their electron configurations are identical. So what it shows me is magnesium's two valence electrons. If it loses those two electrons, gets rid of them, then it would have the same configuration as neon. And so that's what I predict. And I get a magnesium ion. So we can, again, the cool thing about trends in the periodic table is we can say, well, every element in group 2A has two valence electrons. And so we predict that they all lose two electrons to form a 2 positive. So again, I don't have to memorize every charge. What I'll memorize is group 2A forms a 2 plus ion. Now I'm starting to get a pattern. Let's now take a look at some of the negative ions, and then we will create our pattern. So here's the negative ions, and an important idea to remember is that nonmetals form anions. So I just chose two nonmetals. I chose one in group 6A, oxygen. And so here's the electron configuration below of oxygen. And if you compare the two electron configurations, what you notice is the difference for oxygen in oxygen and neon, which is the closest noble gas. Oxygen has 4 in its p sublevel, and neon has 6. So if the oxygen gains 2 electrons, then it would have the same electron configuration as neon. And so that's what the ion is. It's O with a 2 negative for gaining 2 electrons. And the metals, remember, take the same name, but I'll write down the non-metal names. When they change into an ion, their end of their name changes to IDE. Now, every element in group 6A has a 6 valence electrons. So we predict that these nonmetals in group 6A will all add 2 electrons to their electron configuration and form a 2 negative ion. So selenium, which would be the selenide ion, I can just know, but as being in 6A, it forms a 2 negative ion. So the idea is not that we have to memorize every ion, but we use the periodic table, memorize the pattern, and then we can predict the common ions of the representative elements. Let's look at one more, which is in the halogens, group 7A. I chose fluorine. So again, looking at fluorine's electron configuration, it has 5 valence electrons. It would need 1 more to be like neon. So that's what it does. It gains 1 electron, and so it becomes an F negative ion, which is called fluoride ion. Remember, a fluorine is the atom, but the negative ions, they take a part of the beginning of the word, and it's not consistent, so we kind of have to expose ourselves and practice, but it's a fluoride ion. They take the beginning of the element name and change the ending to IDE. And so all of the halogens have 7 valence electrons, and so we predict that they would all gain 1 electron to look like the noble gas closest to them. So let's figure out the other ones. The transition metals, they cannot be predicted using the octet rule. We'll talk more about them in a future chapter. So these we're not going to predict, but all of the representative elements, we can think about their valence electrons. So group 3A with 3 valence electrons will lose all 3. And so a common one we see is aluminum, and it would be a 3+ charge. I'm going to skip 4 for a minute. We'll come back. Once we get to nitrogen at 5A, it's going to start gaining electrons, these nonmetals, and so it forms a 3 negative. We know the noble gases are not going to form ions predicted by the octet rule because they already have a stable electron configuration. Now in group 4, some periodic tables books leave it empty. I like patterns, so at 4, it's like the transition. With 4 valence electrons, you could lose or gain. What we would predict is that metals would lose the electrons and nonmetals would gain. What we will find practically is that the nonmetals like carbon and silicon, they're very small. Remember, elements at the top of the periodic table, especially those to the right, are small, and they are not very stable with a 4 negative charge. So while we'll predict it, we don't really encounter it too much because it's not stable. So I just wanted to erase that. But we'll predict it based on the octet rule, but we don't encounter it, right? It's not one of the common ions that we will encounter. So this is the pattern. Across the top of the table, this is what you want to learn to predict the charges of ions. So I have one last slide that we're just going to do that so you can see how you would apply this pattern. So I have a periodic table here, and I'm going to write my predicted charges across the top. Remember, we're not going to predict for the transition metals. They don't follow the octet rule. Okay, so that's my charges. This is what I would predict. So what I do, and I'll show you one. If you want to pause it and then you predict the others, you can. So calcium is letter A. I find calcium. I see what group it's in. That group is predicted 2A. So the charge is 2 plus. That's what I would predict. And this says, this is not, I'll have to fix my slide. Write the formulas, I should say, for the ions. I haven't had the luxury of going through these slides once with the class, so I'll have to change that. But predict the formula for the ions is what that should say. So calcium 2 plus, I'm going to write its name. This is the calcium ion. Okay, now selenium is Se, so I find it over here. It's in group 6A, which is predicted by our pattern to be a 2 plus. So selenium 2 negative is what I would predict. And this is selenide. Because it's a negative ion, they change the ending to IDE. Potassium is an alkali metal in group 1A, and the writing's getting kind of mushed in here, but that would be a 1 plus. The metals are named the same as the element. So this is a potassium ion. Bromine, which is over here, we would look. It's a 1 minus. All of the halogens are. So it's Br negative. We'd call that a bromide ion. And then aluminum, which is right here, we would look, that would be a 3 plus. That's the aluminum ion. So this is going to be a very helpful pattern for us to use. In future chapters, we often have to know the charges of the ions of our representative elements. And so you learn the pattern. Okay, learn the pattern, and that will help you predict the ions.